we are going to discuss some important definitions that you will come across when dealing with sequences. And the first one is we say that a certain sequence is increasing when, like from this word itself, you have the meaning, right? So the sequence terms should increase with n, right? So the term on the right hand side should always be greater than or equal to the term on the left hand side, right? Now sometimes when you say increasing, they will use the strict inequality, and for this greater than or equal to sign, you call it as monotonically increasing or monotonically decreasing. Or sometimes people use this greater than or equal to sign for just increasing, and if they need the strict inequality, you explicitly say that it is strictly increasing, right? So that will depend on the context, but for our study purposes we will consider this greater than or equal to sign when you say increasing, and this less than or equal to sign when you say decreasing. Now see, here in the left hand side you have an, here in the left hand side you have an plus 1. We will do an example. Now if we consider this sequence 3 over n plus 5, right? Now you can see the an term is this one, and how about the an plus 1 term? That means we have to replace all the n terms by n plus 1, right? So it will be plus 5, that means 3 over n plus 6, right? Now at once you can see that the numerator is the same, but the denominator in here is less than the denominator in here, because here you have a larger value, because n is the same and 5 is added here and 6 is added here, right? So this has a larger value, that means this is small, right? So in other words, we can represent that inequality like this. So which means our sequence decreases when n increases. Now if you need to prove this like in a precise way, what you can do is, now this is the statement that you need to prove along with the inequality. Now this is something else. Now for these inequalities, if we say 5 is equal to 6, this is false, right? This is false. And if we say 5 is less than 6, this is true, right? And also we can say that 5 is less than or equal to 6. This is also a true statement, okay? So in place of a strict inequality, you can even have a this equal sign as well. And here for now, if you say 5 equals 5, that is true, right? And if you say 5 greater than 5, that is false. But we can say this one, 5 greater than or equal to 5, that is true. Okay, so these are some subtle changes that you might get confused. So now here we exactly know that you have a strict inequality, but still you can have a equal sign as well, right? Now anyway, if you need to prove this result correctly, like in a direct way, what you should do is you just have to you can just write down the two terms separately, right? Now here this is 3 over n plus 5, and then this will be 3 over n plus 6. and then to obtain this one, you can do a back calculation. Right? That means you start from the answer. Okay, now this is the answer you need to obtain, and to obtain this answer, what should be the next immediate step that you need to have? That means we just plug in the correct values. Right? Now if we have this one, we can obtain the answer. Now what do we need to have this one? Then consider the next the step that should satisfy in order to give this one as the answer. So underneath this one, what you can have is, you can just cross multiply the two. 3 here and 3 n plus 5, and then you can just cancel these 3's, so you will have n plus 5. And now since these are additions, you can even cancel the 2n values, so you end up with 6 greater than 5. See, now this is a true statement. Okay, now what you can do is, you can start from this statement and go to this step, and then from there you can go to this step, then you can take this one, and then ultimately you can prove this condition. So starting from this one, you can prove the given result, right? So now if I write the answer only, now to prove this one, an is greater than or equal to an plus 1, that is this one. So to prove this one, we can start with this known result, and then you can add n to both sides, and then multiply with 3, and then just cross multiply it, and that gives the required result. So this is the way you have to prove such an inequality. Okay, right? So anyway, what we have shown is that we have a decreasing sequence, right? And similarly, you can say that this sequence also decreases. So that means we will need to have this result. The term with higher n value is less than or equal to the term with a lower n value, right? So what you should do is, you just have to plug in the terms appropriately. So n plus 1 will, like for the an plus 1, you just have to replace all the n values with n plus 1. Okay, so we have this one. Now we need to prove this one, and now to do that, you can use back calculation. In order to prove this one, we will need this one. And what do we need to have to prove this one? We just take a step back, right? We can like cross multiply it and carry out the calculation as before. And if you do the calculation correctly, you will end up with this result. So from here, now we know that n is greater than or equal to 1. So definitely this is a true fact. So from this true fact, we can do the back calculation like this, and ultimately end up with an greater than or equal to an plus 1, which says that the sequence decreases. And the final definition is the bounded nature of the sequence. Now we say the sequence is bounded above if we have a certain number which is greater than all the sequence points, and if we say that the sequence is bounded below if you have a number which is less than all the sequence points, and we say the sequence is bounded if it has a lower bound and a upper bound, like if it is bounded above and below. So for example, if we take the sequence an equals to n, and we can represent it like this. So the sequence points in this sequence will be 1, 2, 3, 4, likewise, right? So you can see all these sequence points are definitely greater than or equal to 0, right? In other words, it is bounded below. You have a number which is less than or equal to all the sequence points. In this case, simple m is equal to 0, right? You can even consider any other number as well, right? Like say, for example, let's take negative 10. That will also work, right? We just need at least one number, okay? Right. So, but the thing is, here you don't have any upper bound, okay? Now, you can see that this sequence goes to infinity. So, we cannot have any restriction from the upper side, from above. We don't have any upper bound. But if we consider a sequence like 1 over n, right? Now, if we consider our sequence as 1 over n starting from 1 to infinity, you can see that the sequence points will start at 1 and go up to 0 in a decreasing manner. So, this sequence will have both a lower bound and a upper bound. So, all the sequence points will be less than or equal to 1 and definitely greater than or equal to 0. So, this is a bounded sequence. This is the upper bound and this is the lower bound, right? So, in fact, this becomes a bounded sequence, right? So, that's what we mean by a sequence being bounded. So, there are two categories. One is the upper bounded above case and the other one is the bounded below case. And if both conditions are satisfied, we say that the sequence is bounded. If we just mention that the sequence is bounded, that implies that the sequence is both bounded above and bounded below.